Hello everybody, so this is Bite Size Chemistry part 4 actually, and last of it now for chemical bonding. So we're going to look at 2008, 2007, we'll start with 2008 first, question 5. And you're asked in this question here to use dot and cross diagrams to show the formation of bonds in magnesium chloride. Now, we go to magnesium and we go to chlorine and we'll find out what's the word I'm looking for there, guys, is their valency, and we can go from there. Now, before you do any of these, okay, if you're not sure whether it's ionic or covalent, okay, it's very simple to figure this out. Go to electronegativity and get the difference. So we have magnesium and we have chlorine. And if you look at your electronegativity tables there for magnesium, it's going to be 1.2. And for chlorine is going to be 3.0. And your difference, if you do it there, and again, you can throw on your calculators there if you want this to be sure. I often do it myself, but you want to get a difference there of 1.8, okay, which is fairly clear in this case here. So your difference 1.8. Now, what did we say before about your electronegativity? If it's greater than 1.7, then it is ionic. Okay, so therefore Mg, or we actually don't know how many chlorines are there, yes. Therefore, we're just going to say it's ionic. So straight away now we don't need to be worrying about the VSEPR shapes. Another way you can figure out if it's ionic or covalent is an ionic bond will always be between a metal and a non-metal. Magnesium is a metal, chlorine is a non-metal. Now, next, we have to figure out what's the story here. Now that we know that it's ionic, what's the story with how many magnesiums and how many chlorines are going to be present. Okay, so I write down magnesium here, and we'll write down chlorine. Okay, and we'll put in our little 2's now once we figure out that. So if we go to magnesium, and you'll see there it's in group 2. And if you go to chlorine, it's in group 1. So metals always want to lose an electron. So magnesium wants to lose 2 electrons to be stable. Chlorine wants to gain 1 electron. So therefore, there must be 2 chlorines present, if that's the case. Okay, so magnesium loses 2 electrons, and a single chlorine will take 1, and another chlorine will take 1. So we write it down as you do for your ionic bonding. So you do Mg, you do your 2 over here. Again, we only care about the what's the word I'm looking for? I'm gonna get rid of those, sorry. We only care about the outermost orbit. And if we're going to put in our chlorine, so chlorine is going to be our X's, and it robs 1 from magnesium. Okay, now you have to put in the charge. Magnesium has lost 2 electrons, so therefore it's now going to be 2 plus. A chlorine has taken 1, so therefore it's going to be a minus and a minus. Now, there's 2 mistakes that students make here. The first mistake being the charges. They forget to put the charges in it. Okay, so just be careful with that. If it's losing electrons, it's becoming more positive because electrons are negative. A single chlorine takes 1, and another chlorine takes 1 here. The second thing they do is they often put a plus in front of here. And if you do that, what you're essentially saying is this ion plus this ion plus this ion. But that's not what we're trying to represent. We are trying to represent what this looks like. You talk about show the formation of bonds. We're trying to show what the bonds would look like. Okay, so that's it. That's all you need to leave it like that. Okay, the bonds are already there. So do not put a sign in between these. Okay, so look, that was D. Let's move on to E. Explain the term intermolecular forces. Okay, we said it already up here, I think we did. It's gone back up a bit. Here we have it. Intermolecular forces is forces between molecules. And look for the E and the E here. Okay, forces between molecules. Next, I'm just going to write it down just so that we can keep track of everything. Forces between molecules. EF. How many is there? G. Okay, grand. Use your knowledge of intermolecular forces to explain why methane has a very low boiling point. The relative molecular mass of methane is only slightly lower than that of water, but water is much higher. Suggest a reason for this. Okay, well, very, very, very simple for this. Okay, there's only 3 types of intermolecular forces. Get your figure out which force it's going to be, and if it's methane, it's probably going to be very, very low in terms of the forces. So we're going to say it's going to be van der Waals, or you could say it could be dipole-dipole. It doesn't really matter. So methane is van der Waals. Bonding. And we could check it, or weak dipole-dipole. Okay, it's a very simple check. All you need to do is go back to your electronegativity values. And again, if you're going to say dipole-dipole, make sure you put the word weak in front of it, just to be sure. Okay, so weak there. But anyhow, how to check if it's van der Waals or weak dipole-dipole? It just goes, methane is CH4, so carbon and hydrogen. So hydrogen is 2.1, and carbon, the electronegativity value of carbon is 2.5. The difference is 0.4. Oh, no, not you, Siri. The difference is 0.4. And remember, for your electronegativity values, if it's 0 to 0.4, it's non-polar. If it's 0.4 to 1.7, it's polar. So when it hits on 0.4, it could be either van der Waals or weak dipole-dipole. And I'll tell you why. Okay, and this goes back to the very first video of me explaining chemical bonding overall. Okay, so getting back to it, if it's non-polar, for the intra, then that usually equals van der Waals. Inter. Okay, and then if it is polar, and again it's polar covalent, non-polar covalent, then that usually equals dipole-dipole. Now, obviously, we'll have to check there now, guys, if hydrogen bonding is coming into it, which it is for water. We'll explain that now in a second. So intra, inter. Okay, so that's how I did it. I got the difference, and I found it 0.4, which technically could be either be van der Waals, or it could be a very weak dipole-dipole. So it doesn't matter which one you say, and then you can specify even further over here. Okay, it's going to be how I got from how I found it was van der Waals, or how I found it was dipole-dipole. You didn't have to in the exam, you could have just said it was van der Waals or weak dipole-dipole. But I wanted to show you how I got to that knowledge of it being van der Waals or dipole-dipole. Water, and you just say it, water has hydrogen bonding. Okay, that's all you need to say. So look, we have F done there now. G. The diagram shows a thin stream of liquid from a burette. A stream of water is deflected, whereas a stream of cyclohexane is undeflected. Account for these observations. Again, it's got to do with polarity. If it's polar, it will be deflected. If it's non-polar, it will not be deflected. So therefore, water is polar and cyclohexane is non-polar. So that's all you have to say. Now, next, explain what would happen in the case of the stream of water if the positively charged rod was replaced with a negatively charged rod. So that would change things up a bit. Well, all you need to say there for this is that the stream of water will still be attracted to the rod, as what will happen there is the molecules will rearrange themselves towards the positive rod. Okay, so way back when, over here, if I can find it there, guys, very quickly. 18, was it 19? It probably wasn't. I asked you to learn off something. Probably 15, no, 13. Here we go, 13. When a charged rod is held to a thin stream of water, the stream is deflected. Why is this? Okay, a charged rod attracts the opposite charge in the water, which is polar. So all you need to do is state that again if you wanted to, for down here. Okay, the stream of water is still attracted to the rod as the dipoles rearrange themselves. Okay, last question, so guys, 2007 question 5b, and again we're asked what's the chemical formula for hydrogen sulfide. Okay, so we don't know exactly what it is. Now we can have a guess. Hydrogen sulfide, so that means there's going to be hydrogen in it and there's going to be a sulfur in it. Okay, so go to the periodic table there, and if you go to the periodic table, you'll see sulfur in group 6. So therefore, sulfur wants 2 bonds, and if that's the case, there has to be 2 hydrogens. So it's going to be H2S. I put the hydrogen first simply because it said hydrogen sulfide. Okay, that's why I put hydrogen first. So there has to be two hydrogens for sulfur. Draw a dot and cross diagram of it to show the bonding in hydrogen sulfide. So that's grand. Ask yourself this: if it's ionic or covalent. I actually already know it. It's going to be covalent, and you need to, if you're not sure, you need to get the electronegativity values and figure out if it's going to be ionic covalent. But in this case here, it's going to be covalent. So write down my sulfur here. Grand. Now I know I have, for sulfur, it has 6 electrons in its outermost orbit. So it needs 2 more, which are going to be from the hydrogens. So that means 6 take away 2 is 4. So I have 2 lone pairs present. And we're doing like a rabbit ears here. You don't have to put a ring around them, but I find it helps. And then I put in my hydrogens here, guys, at an angle. And that's it. Okay, that's what it looks like to show it. Would you expect it to be linear or non-linear? Okay, it's going to be non-linear. Okay, then you have to say why. Okay, then again you just write out how many lone pairs. This is just accounting for the shape, that's all it is, and how many bond pairs. 2 lone pairs, 2 bond pairs. Okay, that's all you need to say. To be honest, as soon as the lone pairs, I should say, come into it, it's no longer going to be linear ever. Would you expect hydrogen sulfide to be soluble in water? Explain your answer. Well, we have to figure out if it's going to be polar covalent or non-polar covalent. So H and S. We know hydrogen is 2.1 just from practice, from the last few of them. What is sulfur? Is 2.5. Difference is 0.4. Okay, so it's kind of in a grey area here. Okay, so you have 2 answers you can write. You can either write no or slightly, and again you must reference the word slightly for this one. Soluble in water. So this is a grey area, and that's often the case with chemistry, especially when you get to a difference of 0.4. So the difference is 0.4, so you can either write no, or you can say it's slightly soluble. And this is your answer already. You already have it. Okay, and that's it. Okay, if you say no, by the way, just to clarify what the answer is going to be, you say it's H2S is non-polar. Grand. If you say slightly, then you say H2S, okay, is polar covalent. I should be writing covalent down here too. So that's it, guys, for the bite-sized chemistry videos. I hope they helped. There is a bit of learning out there for sure, especially for the definitions and anything to do with the water when it does come up, you know, the water deflection and so forth. But the rest of it, like, it always comes back down to electronegativity. Use it to figure out if something is polar covalent, non-polar covalent, or ionic. And once you know what it is, you can figure out what type of intermolecular bonding it is then from that. And again, if you're unsure, go back to my very first video explaining the concept of chemical bonding and so forth. Okay, everybody, I hope you took something from that, and all the best with your studies.